Hello, everybody. It's good to see you again, and I hope you had a reasonably good week. It's Friday, and with that, I think we're going to end the week with some math. Welcome to this daily live stream where we will talk about math in an improvisational way, where there will be all kinds of different questions coming from the audience. I see people have said, "Yay!" Yes, I'm also very happy to be here. As some of you know, I've been working on finishing up an app, so that's where I was just now. But we just put everything together, almost done with the app, and also at the same time, I managed to come onto this live stream to say hi to everybody. Now, as some of you may know, if you have been here with us before on this live stream, we will be talking about a wide-ranging set of topics in math. I like to get these topics from the audience. And the kinds of questions that I will answer will not be the kinds that your teacher is answering, because you already have a teacher. Instead, what my goal is to go and get inspired by some of the things you're talking about, and maybe find an interesting angle that a mathematician might have when when a mathematician sees what you write down. Now, I know from experience that the main topics that people have been studying, that among the people who come to this live stream, are around algebra and geometry. So I'll always try to make my answers understandable to people who are studying algebra or geometry. Now, this time, because it happens to be also, I don't know, maybe I guess because it's the end of the week, I would also like to do a really quick poll. I'd just like to know, what kind of math are you taking? Because I haven't asked that question for a week, and I just want to see if that has changed. So if you don't mind, we have an interactive live chat, and that makes it fun because then I can see what you guys are thinking, and I see what you're saying at the same time. So if you wouldn't mind, please let me know what kind of math you're taking right now. Whoa, that was quick. I see all kinds of things coming in. So I really do see a lot of algebra. A lot of people are studying algebra and the topics around there. So in that case, let me get my pen. In that case, we're going to go indeed and try to cover something in this area. All right, let's go ahead and get started. What kind of questions might you have? I'm very curious, and you're welcome to type either in the chat or well, I guess there isn't really an or, so just please do type in the chat. Let's see. Oh, wow, okay, I already see something that came out. Huh. Pom Pon Wang asked, how was pi discovered? That's a good question. I'm not sure. I think what happened is that at some point some people were hungry, and they realized that if you take like a crust and put some fruits inside, it tastes really good, and then that person discovered pi. Oh, I understand. You're asking a different kind of pie, the kind of pie that you might ask on a math live stream. Okay, so how was that pie discovered? I think it's because somebody baked a pie and was kind of curious how much pie they had. Well, I think it's actually quite natural. You see, if you want a real answer to that question, the real answer to that question is that circles are really important shapes. They're kind of hard to draw, but let's pretend that's a circle, okay? Maybe that wasn't such a bad circle. But circles are really important shapes because they're very easy to define. I could just say a circle is something where there is a center, and I make sure that I draw all the points that are the same distance from the center. That's like the easiest kind of shape to describe. I mean, come on. If you're supposed to describe a star, what's a star? I don't know. Maybe a star looks something like... That's hard. Is this right? As you can see, I'm having trouble. Oh no. Okay, this kind of star I can draw. This kind of a star I can draw precisely because it's actually mathematical. So this is a star, right? But I mean, this might not have been the star that you were thinking of. But anyway, it's a star, and I could sort of draw it. It's actually kind of not a very, it's a kind of a lopsided star. But it's like, it's a star. But it's very hard to describe exactly what this is compared to just saying a circle. So then how was pi discovered? It was that people wanted to be able to figure things out about circles. And at some point, they realized that when you took the area over the radius, over the square of the radius, it was always the same thing. Is that what they did? Actually, probably not. Probably what they were doing is they measured the circumference divided by the diameter. Why do I say that? Because, how would you even find out the area of a circle anyway? Here's an interesting question. Like suppose somebody told you, I have a definition of pi. Pi is called the circumference of a circle divided by the diameter. How would you estimate this? This is actually what people a long time ago had to do. What would you do? Using pi, says TempID. That's right, you'd bake a big pie, but you need a circular thing. How could you actually get a big circle? Does anyone know a way that, let's pretend it was ancient times and you have to get a big circle. How would you get a big circle if you want to go measure the circumference of the circle divided by the diameter? Use a string. Exactly, Sandy Matthews, that's a good idea. You could use a string, and you can put a string on the ground, and if it looks like this, then you kind of like push it open, and you push it, and you push it, and you push it, until it looks like more circular-ish. Is that what you mean? And then you get like a bunch of people, and the people all pull as hard as they can, and eventually it looks sort of like a circle? Is that the idea? So, this doesn't seem that efficient, by the way, because I don't really know if that's really a circle. That's sort of like if you're trying to make a pizza, like throwing a pizza in the air. How do you know it really became the pizza? Well, I see. This V4913 says this is like hashtag string theory. You guys are funny. Okay. But no, that's not really what you do with a string. Actually, if you had a string, you would put the string on a circle. Oh, right. That's what you mean by string. So what you mean is first find a circle. Now you find the circle and you put the string around it. That's exactly right. And you're right. So if you have the string, if you have a circle and a string, you're in good shape. But where do you get the circle from? That's the next question. Where do you get the circle from in the first place? I'm just sort of saying, suppose you know that there's going to be a circumference divided by a diameter. How do you find a great big circle to use? Does anyone know how you would find a circle? A pie. Yue Deng says bake a pie. But you need a circular pan. Draw one, says cookies and cream. But how do you know you drew a good circle? Carve it. A wheel. Wow, that's a neat username. But you said a wheel, but how do you get the wheel in the first place? I mean, I'm actually asking, how would you get a circle? Your face. Maybe. Depends on what your face is. I actually haven't seen... yes! Christmas Warrior says, you draw a point, and you make the string, and you use it like a compass. Exactly. So that's actually how you could get a big circle. You go and stick a pole in the ground. Right here, there's a big pole. Then you get your string. And you make the pole, a pretty narrow pole. Okay, it's a narrow pole, but it's a strong pole. And you get a really, really long string. And what you do is you just go around the pole. And as you go around the pole, your string has the same length. You go around the pole with the string being the maximum length. And pretty soon, you've just done what you normally do with a compass. And again, I can't draw very well. Whoa, that's terrible. Let's try again. Let's pretend that was a circle. Okay? This one's close enough. I want to give you a tip. Here's something that I learned the first year I went to the US National Math Olympiad training camp. The thing I learned was, it is very hard to draw a circle this way. It is a lot easier, if you ever have a center of the circle, it is a lot easier to draw the circle first. You draw the circle first, and then you put the center in the middle. That is a sneaky trick. If you ever want to make something look like a circle with a center, draw the circle first and you'll be in good shape. Okay, right. But with that string, you're able to make a pretty good circle. No, that is an egg. Right. So you're able to make a pretty good circle. And then you could use another string, or even the same string, to go and measure all the way around. So that is indeed how you would measure pi. And that is probably why most people said that they will use the circumference divided by the diameter. And that makes a lot of sense. So it would be quite reasonable, because this is something I can do. I can imagine somebody sticking a big wooden pole in the ground, and then just like going with a string all around it, and then you could estimate pi. Now, remember when I started this, I started off by saying, hey, you could also have used the fact that the area is pi r squared. That's another way to get pi, right? So one way to get pi is the definition. This thing over here is the definition. There's also a corollary, or there's a consequence of the definition, which says that pi is also the area of a circle divided by the square of the radius. Now imagine that you're like from 2,000 years ago. This one is not that hard to calculate, the circumference of a diameter. You could do it. You just need a stick and a string. On the other hand, how would you calculate that? Suppose somebody asked you to go and figure out what is, like you could go draw this circle if you wanted. How would you even find the area in the first place? Does anyone know how you'd find the area if I just had a circle like this? How would you find the area? Looks like a slice of pie. You guys are great. I mean, suppose I just had this area, right? I got this circle, but area? You know, like we just saw that the circumference was easy. Just get a string. Divide into small triangles. But can you really do this? Imagine it's like 2,000 years ago. How would you accurately even find it? Use water, says Athena Wu. That's a pretty clever idea. Actually, that's a really clever idea. And that's better than what I was going to say. So let's use Athena's idea. Athena's idea is use this thing to make a circle and then make like a circular pan. What do I mean? So now we know that it's possible to make a circle. With that circle, go and make like a pan, sort of like a deep dish pizza pan. Like this. Do you guys know what I mean? I could go and make a circle pan. You know, like, oh wait, is that what things should look like? No, actually, if I wanted to do a proper drawing, it would probably look like this. There. Now it looks sort of like a better drawing, right? So what I have is I have a pan, and I could fill the pan with water. Oh yeah, there are two ways. Christmas Warrior says take the pan and put it in water. Or you can put water in the pan. It's up to you. Either way is fine. But when you go and put the water in the pan, or the pan in the water, then you can find the volume. And once you know the volume, all you have to do is divide by the height, which you can also measure with a string. So the easiest way, if I had to go and find the area of some circle, the area of some circle, I would turn it into a volume problem, and then just divide. And the value of the value of using volume is that with water, I can easily pour water into a rectangular container. I could take this water and pour the water into a rectangular container, where the rectangular container looks like this. And if I have this rectangular container, I just see how much up it goes, and the volume will just be like length times width times height. Okay, so that was what I thought about when you guys brought up pi. As you can see, these are the kinds of answers that are just kind of coming up as a mathematician looks at the kinds of questions that you guys ask about. Neat. I think this is neat too. Okay. Diane Zhao asks, what is the question? Yes, that is the question we're trying to solve right now. What is the question? What is the next question we want to talk about? The Fun Masters, how come you so good at drawing? I'm not good at drawing. In fact, I'm terrible at drawing. There are only a few things that I can draw well. One of the things that I can draw well is called a straight line. You like my straight line? Actually, I like that straight line quite a lot. That's a line. I can do a line. I can also sort of draw circles, right? Drawing circles, you just go in a circle. And that's about all I'm good at drawing. And that's also because I'm a mathematician. As a mathematician, you can do almost everything. Actually, that's completely false. But you can do lots of interesting things with lines and circles. In fact, the entire subject of geometry, especially if someday you go and play with the math competitions like Math Olympiads, when you go and learn about geometry, you get all these interesting facts where all you need are lines and circles. So, the things that I got the most experience drawing were just because as I was playing with all of these math problems, I found myself drawing lots and lots of circles and lots of lines. Okay. Actually, while I have lines and circles, can I tell you something cool? Yeah, I can tell you something nifty. Something nifty with lines and circles that just came to my mind. You like my line? Thank you. Thank you very much. Let's do something else. Let's do something where I'm going to draw a circle first, okay? And now it's going to be a little tricky because I'm going to draw a whole bunch of lines. So I'm going to take this circle. I'm now a little bit worried that I drew a circle that was too big. I'm going to make a smaller circle because I need to put something else in. So here. That's a circle. Now there's some interesting things you can do with lines and circles. Now I'm going to draw a line that goes and it's called tangent to this circle. What that means is that the line is going to touch the circle at exactly 1 point. There we go. That's a line. And I'm going to draw another line, which is also going to touch the circle at exactly 1 point. For this, I'm going to turn my tablet a little bit. It'll make it easier to draw the line. Okay, that was not bad. So I just did this. And there's something else I also want to draw. I want to draw the center of the circle. As you can see, that's why I drew the circle first, because the center is easy to draw. Now that I've drawn the center of the circle, I want to connect the center of the circle to this point. I'll do it like this. Does anyone notice anything interesting about these angles? What do you notice about those two angles? 100. Coconut. What else? What do you know about these two angles? The two angles that I've cut this into. They are the same. They're equal. Thank you very much. Yes, all of you have noticed that they're equal. And there's a good way to tell that they're equal. It's because the whole diagram is symmetric. That's why we like circles. And Ivy He said the word congruent. That's the fancy way of saying that the two angles can be moved from one to the other with flipping if necessary. But so somehow we have these two angles which are equal. And that's really neat. Actually, this is what's called if and only if. If I didn't draw the circle, but if I just drew this line, it's actually called the angle bisector. If I drew this green line that goes through the middle, actually that green line definitely goes through the center of this circle. But now you can also do something else that's interesting. Suppose I go and take one more line, and I make one more line. It's not supposed to be a symmetric picture or anything. I just make one more line that goes through like this. Okay? And it's also tangent to the circle in another way. Now I'm going to ask, what do you know about this line? That line actually also cuts that angle into two parts. Let me do this. Oh no, that was a mistake. I used the eraser by accident. But thank goodness we have undo. It's back. Okay, so now let's go back here. I will say, after I started teaching with this instead of the blackboard, I realized that the undo feature is pretty useful, because on the chalkboard somehow I can't really undo. On the other hand, then again, on the chalkboard you wouldn't accidentally put your eraser down and suddenly all the lines disappear at the same time. Okay, great. So I'm going to draw that line again. This is not the eraser this time. It's also going to cut that angle into two parts. Yes, thank you. This is indeed a circle inscribed in a triangle. What I'm showing is that if I draw these lines, these are the three lines that break each angle in half. You know, in theory, I could go and take this line, which breaks that angle in half. I could take another line cutting that angle in half, and another line cutting that angle in half. But guess what? They always all touch at the same time. Actually, that's what this proves. Let me erase the circle now. Poof. What I've just proved to you is that if you take any triangle and you cut every angle in half by drawing these lines, all of those lines will actually always definitely go through the same point. The first time I learned this, I thought that was cool. It's like, of course, two lines will eventually intersect as long as they're not parallel, right? But these aren't parallel anyway. So these lines will eventually intersect. But to have three lines all intersect at the same time, now that's very unusual. If I just go anyhow draw three lines, they will probably not intersect. But what this is showing is that because I had the circle as helping me figure this out, I've just proved that if I take any triangle and cut each of the angles in half, boom, all those lines intersect. Let's bring the circle back with another undo. And so, yes, I will say that these circles and lines, those seem to be the only things I am pretty good at drawing. So thanks for your compliment, but unfortunately it's only because I'm drawing lines and circles. What else can we talk about here? Dayit asks, how can I study for math counts? So Dayit asks, how can I study for math counts? Here's what I'd say. It's great that you want to study for math counts. Math counts is a really fun set of questions that you can play with. I would say to think about some of the old questions is useful. If you want to find some systematic way, ideally you would find something that will help teach you the fundamental concepts, and maybe those concepts can be even systematic, like in some order. However, I would give the advice that you don't prepare for math counts just by trying to find places where people will show you how to do all the problem types. That's not the interesting way. The interesting way is if you actually get to fight with the problems as you're learning. Sort of like what I'm experiencing here. People ask me questions and I'm like, how would I figure this thing out? And that's what you're watching. And my encouragement to you is whenever you want to learn something, find a way to learn it where you can have people, give you enough time to think about it instead of just having the answer given to you right away. Actually, regarding math counts, we might have something pretty fun coming up soon. Actually, I'm talking with the people who run math counts. As you know, the National Math Counts competition this year was unfortunately cancelled, and that's because many things in this world have now been cancelled. But, the National Math Counts organization is really trying to do a lot for education. And so we might be working together. Stay tuned. There might be something interesting coming up on these daily live streams in the future. More questions? I'm actually looking at all of these questions because they're so interesting. Okay, Athena Wu asked a question which is about coronavirus. Suppose you found a cure for coronavirus. How would you distribute it? Because you don't know if the person you're distributing it to is infected or not. So that's actually what makes it so difficult. It's that somehow if there's a cure, the cure you can only give after someone has had the coronavirus, which is maybe too late then because they could have gotten some other people sick. I would say for that kind of a situation, if you have something to help, if people are already sick and to help them get better, of course you use it at the hospital's point. But then what you also need is you would need some very efficient way to find out who else might be sick. So it's like if you have a cure that works only after people are already sick, what you then need is a very, very good way of saying, oh, this person is sick. I need to know who else they've seen like in the last few weeks, last like week or two. And then if you could go and find those people, you'd be able to more efficiently distribute your cure. That's one thing. The other direction would be to make a vaccine. The vaccine you give to everybody. But that will also be difficult because your vaccine, if you give it to 7 billion people, as we talked about on a live stream earlier this week, it better be very, very reliable. More questions. What else can we do here? Kelly Wang, how do you know so much? I don't know. I wouldn't consider that I know so much. I would consider that I have a few important facts, like the speed of light, like how gravity works, like angles, what's an angle and what's a bisector. I actually, in my head, I don't have lots and lots and lots of knowledge. In fact, I'm able to efficiently do a lot of questions by having less pieces of knowledge stuck there. But instead, I have a lot of practice trying to figure out what to do to put together the little pieces that I have. This is something I learned, in fact, when I was teaching my math class at Carnegie Mellon University. So here at Carnegie Mellon, the way I teach one of my math classes, which is the one in the fall, is one where I just put questions up and people can suggest any idea that they might think of for solving these questions. And that causes me to be stuck standing in front of the room, in front of like 50 people or 100 people, having people say ideas to me, and I have to think about them right away and think about how to put it together. It's very different from my usual way of teaching a normal class. When teaching a normal class, you're like, well, I know what I'm going to prepare. I already prepared. I know what I'm going to say. But this taught me how to kind of always stay on my feet. And by staying on your feet, you can go and take some very simple basic facts and put them together whenever you need to. So the answer is, it's not that I know that much. There are people who know far, far more than me, people who have memorized lots and lots of different facts. On the other hand, I would much prefer that I can put facts together. And I encourage you, if you like what you're watching on this live stream, you should be able to see that usually what I end up doing whenever I have to answer a question is I go and grab onto a few things that I know and figure out the rest as we go. Okay, more questions. Aha. I see. So this is very, very interesting because I see some people asking things like, what is a wormhole? A wormhole is something that you'd find in the ground and you can see them more easily after it rains because the worms come out of the holes. I think you mean the physics version. This is now something where I'm not sure that I know for sure that these things exist, but they might be the consequences of certain theories that somehow space and time have some curvature, and maybe there could be two very far away parts that are close together. Again, I'm not an expert on this, but my vague understanding of it would be like this. Suppose you were an ant, like the ants with like 6 legs. These kinds of ants. Whenever you draw an ant, you do something like this. I guess you might need some antennae. Oh no, now it looks like it has 8 legs. Whatever. So this is an ant. So when you have an ant, from the point of view of an ant, ants just kind of crawl around. They don't really understand that there are 3 dimensions. And so if you had an ant, you could in theory have the ant on like a big blanket. And the ant would just be crawling on the blanket. And as far as the ant is concerned, it's just like a flat thing. But you could imagine that somehow the blanket, you might be able to have like the blanket loop on itself. I don't know if I'm going to draw a picture. It might not make any sense. But I'm going to draw a picture which is like, see the ant here? And this is like a 2D version. Here's the blanket, and the blanket kind of loops around. Okay. What I'm trying to draw here is that I'm kind of like looking at it, and the blanket is going up, around, and back around here. So the blanket is a 2-dimensional object. Oh my gosh, Time WW Brody got the ant emoji. I didn't even realize that there were ant emojis, and Sing Lee's got one too. So we're going to be crawling in ants soon. Anyway, so we got all these ants. We got an ant, and it can go along on that blanket all the way around. As far as the ant is concerned, there is just a blanket. But, you know, maybe somebody decides to play a trick on the ant and kind of makes a little tunnel here. You could imagine that. I mean, again, the surface is up here where the ant is, and the surface comes back down around here, and you could imagine making a tunnel, and somehow suddenly the ant can go from all the way over here to all the way over there. From our point of view, the ant didn't go very far. From our point of view, the ant just went like, pop, it's over there. But from the ant's point of view, the ant had no idea that there was going to be this little hole there. From the ant's point of view, if it crawled all the way around, it would be like thinking, gosh, I've got to crawl all the way back. But somehow this wormhole makes it so that the ant can get through. Why is it called a wormhole? Because it's kind of small. Unfortunately, maybe the ant won't even fit through. So all the ant can do is say, wish I could squeeze through this thing and be over there. Okay, that is my vague understanding of this, and the idea that somehow space and time could be curved in the sense that we have some way of looking at the space around us. However, you never know. It could be like an ant which can only see in 2 dimensions. Ants can only imagine 2 dimensions, except that the ants really in a 3-dimensional space. Okay, more questions. Wow, so we have a question. Yitong Lee asks about speed, time, and distance. Can you explain speed, time, and distance? When I think about these things, I just think about what they're called. Okay? So the way I think about a lot of these concepts, and the way I survived high school physics, which is not what you should do, was I always think about things in terms of their units. Does anyone know what you use to measure speed? What do you measure speed in? Do you measure speed in liters? No. Do you measure speed in watts? No. You measure speed in, well, depends where you live. In America, you measure speed in miles per hour. In other countries, you measure speed in kilometers per hour. In physics class, you measure speed in meters per second. But speed is always something like miles per hour or kilometers per hour or meters per second. Hey, look, it's always going to be a distance over a time. That's what speed means. It's like how far do you go divided by how long it takes for you to get there. So the speed is always going to be some distance divided by some amount of time. That's it. So I've just explained to you speed, distance, and time. And usually the speed, distance, and time problems talk about something like, suppose I'm going at 60 miles per hour. How far did I go in 1 minute? That's what these usually are like. Go at 60 miles per hour. That's what MPH stands for 1 minute. Well, how far? Well, 1 minute, that's how you think of all these things. Speed is like how far you go divided by how much time it took. So I guess I just need to figure out if I'm going at that far for that amount of time, well, 1 minute is only 1/60th of an hour, right? So the way you would solve these kinds of problems is you'd say, I'm going at 60 miles per hour, but I'm only going for 1/60th of an hour. So the answer is 60 miles per hour times 1 over 60 hours. Because that's what 1 minute is. And so the answer is 1 mile. Do I have enough space without crashing into my head? Maybe. 1 mile. Okay, so what is the question? The question is, if you go, well, the question was to discuss what is the relationship between speed, distance, and time. And that's that. But I'm explaining to you that even if you forgot, I mean, don't go and memorize a formula. It's useless. Don't memorize the formula. Instead, go and think, last time you were in the car, what was your speed? Was your speed 63 watts? No. Your speed was some miles per hour. There you go. It's going to be miles over hour. That's how far over how long. And then you're done. And why I gave this, indeed, there is indeed an equation. Speed as rate, d equals rt, that's a formula. A lot of people say distance equals rate times time, if you multiply both sides by time. And that works. I mean, you can memorize anything you want. However, I like to just say, hey, it's just like what the units tell you. You can do a lot of problems by just saying, what units do I have? Oh, it's going to be a unit of distance divided by a unit of time. Then I probably am going to divide distance and time. And this can get you through a lot of physics, actually. I chose this number, by the way, 60 miles per hour is 1 mile, because when I was young, that was when I realized this fact. And it was very nice, because in America, many of the highway speeds are like 55 miles per hour or 60 miles per hour. So then whenever you're going down the highway, if you see a sign that says, Philadelphia, it's only in 382 miles, then I'll be like, okay, I'll be there in 382 minutes. Which, if there's 60 minutes in an hour, it's something like just over 6 hours. 6 hours, 22 minutes or something like that, if I did that right. Not sure. Like almost, yeah, 6 hours, 22 minutes, something like that. But it's nice to be able to just figure it out. And so knowing the 60 miles an hour is 1 mile per minute is useful. Okay. Let's see. What else do we have here? Oh. Okay, Andrew Shen asks, can you explain how to cut a triangle into pieces? Take a piece out and rearrange it so it's the same size. Okay, I know what you're talking about. You're talking about a very famous drawing, which makes no sense, where somebody kind of drew on graph paper. They drew on graph paper. I'm going to try my best to draw it. Again, this is going to be hard now because I don't have a very precise graph paper. Can I get one? I was trying to think if there's an efficient way to get one. I can't think of an efficient way to build one right now. But okay, so if I have something on graph paper, let's try. We draw a few rows. Here's one. Here's another. Right, and then you have something like this. Good enough, okay? And that particular picture, let me see. Can I make this work? Yes, I think this thing can work. No, this thing cannot work. I need another one. So this is this question about how can I take a triangle and cut the triangle into some pieces and rearrange the triangle's pieces and get like a bigger, and get like something which is 1 square less. Wow, that's not a very straight line. And the reason is because I'm now trying to draw this thing. Okay. Oh no, that went away. Let's bring that one back. We need all of these. Yeah, this will be close enough. So this line goes all the way through, like this. Okay. Actually, given that this picture is not drawn to scale, it will not actually be very easy to see. But what I just drew is I drew something where there's a triangle. And the puzzle you're looking at is something where there's a triangle that looks like this. And then what the person does is they go and take this thing and they kind of cut all of these parts into smaller parts and put them all together, and it's like it's smaller by 1 square. And all I wanted to show you is that when you do this, the reason that you can have something that looks very strange is because the number of squares across the bottom is not a multiple of 3. So if you look at one of these particular examples of a drawing where there's this triangle, it's been dissected into some shapes, the shapes are reassembled, and for some reason the new thing has a smaller area, what is actually happening is that in this triangle, I've done one where it's 10 units across the bottom, if I could count. 4, yes, it's 10 units across the bottom, 10 across the bottom, and only 3 up and down. And if it's 10 across the bottom and only 3 up and down, what that means is that the line that goes all the way through should not go through this point perfectly. However, in this version of the fake problem that people are doing, they artificially make it go through that point. So let me draw another picture, which actually just has numbers. Suppose I have 3 this way, and suppose I have 10 this way. Is that 10? Maybe we want more. That looks a bit more like 10, okay? Then what you do is you draw one picture which goes to this point here, which is at 2, 3. This is 2, 3, and you make it go through that point. Here, and then you keep going all the way to the bottom. So this looks like a triangle, but it's not perfect. It's not perfect because the slope, it should be going down 3 units and going across 10 units. Instead, in this part, we kind of made it go down 1 unit and across 3 units. So it's not quite right, but your eye can't tell very well. Then the other thing you do is you also draw another triangle, and the other triangle just happens to go through the point which is here at 7. And that's how I can see this picture is not drawn to scale. You know what? I want to draw a more to scale version. If that's 3, this is going to be 6. Wow, this is so not to scale. Let's keep going. So where should 9 be? 9 should be here, right? This should be 9. Maybe around here. And then 10. So it keeps on going. Maybe that's about 10. Good. Now I'm going to make it go through this one point up here. I'm using something called the big point theorem. If you're going to try to draw a diagram, if you draw your point big enough, it looks like it goes through it. Okay, here we go. That looks like a triangle, except that that's not a legit straight line. On the other hand, in that puzzle you're looking at, when they reassemble it so it goes through this point instead. 7, 1. So instead it goes through this point. Now, in reality, if you look at these slopes, this thing went down by 2 and across by 7. That's going across by a lot. So it's going down by 2 and across by 7. Down by 2 and across by 7 is like going down by 1 and across by 3.5. So this particular slope here, it goes down. Let me put it this way. It goes, it goes down by 1 whenever you go across by 3.5. Now, if you have something which is like every 3.5, it goes down by 1. If you have something here, which is the yellow thing at the 7, that point is actually up here. 7, 1 is actually up here. Does that make sense? The reason 7, 1 is up here is because this blue thing, it goes down by 1 whenever you go across by 3.5. So the blue thing goes through there. On the other hand, the yellow thing, this point, is going down by 1 and across by 3.5. I just realized I flipped around which one was inside and outside. But what I'm drawing for you here is that this thing. So if I went and drew another triangle, where the other triangle goes from that very top point over through this point and then through here, it looks like a triangle. And then here's another one, a blue one, which goes to here and across to there. Both of them look like triangles. So the question here was, how could it be that you have like a triangle that you cut into pieces and you reassemble and you got a smaller triangle? The answer is neither of them were triangles. oh, you're kind of confused. Let me explain this, maybe because you haven't seen the problem before. But what I'm trying to explain is that somehow you can draw two things here that look sort of like triangles. The only difference is that one of them goes through the point that's 3 across and 2 up, which is there. The other one goes through the point which is 7 across and 1 up, which is there. And if you draw these two, they look sort of like triangles, except that because of the slopes, the reason I know that the yellow thing is on top is because this thing from the 7 and 1, it went down by 1 and across by 3. Whereas the blue one, it went down by 2 and across by 7. Down by 2 across by 7 is the same as down by 1 across by 3.5. So the blue one is underneath. And so when I have this picture, at first it looks like these two triangles should probably have area which is close to each other. But they don't. In fact, the difference in area between these two is 1. That's a really interesting fact, by the way. There's an interesting fact, I don't have time to prove it in today's live stream, but if you draw any quadrilateral like this, a quadrilateral meaning it has 4 sides, any quadrilateral like this where all of the points are like whole number comma whole number, actually the area of the quadrilateral will always be at least 1. So there's in fact 1 unit of area in this smushed thing all the way over there. So that I hope answers your question. For the person who asked that question, the answer was they aren't actually triangles. And it turns out that you can squeeze an entire difference of area in 1 in this picture. Oh, why is it not a triangle? Huawei asks. Oh, maybe that's why some people are confused. Look, here's how you can tell. The big blue thing goes down by 3 and across by 10. So I'm going to draw a smaller version. Well, no, let's draw the whole thing. Goes down by 3, across by 10. That's a perfect triangle. But if I wanted to have a triangle, it cannot go through this point, which goes down by only 1 and across by 3, because 10 is not divisible by 3. So in fact, this thing doesn't, 10 and 3 have no common factors, so this doesn't go through any whole number points at all. So the point is that this blue one is not actually a triangle. This blue one is actually a triangle, and these things that look like triangles aren't, even though they happen to go through these nice points. Okay, other questions? What can we do here? Jason Chang asks, how do you remember to divide by 2 every time you find the area of a triangle? I think the word remember is definitely something that people are used to doing, although you don't have to remember, because you should divide by 2. It's because a triangle is half of a rectangle, right? Look. Here is the rest of the rectangle. Why does it keep... Yeah, it keeps doing this because, again, I'm doing a lot of these live streams. But yeah, here's the other part of the rectangle. So a triangle is half of a rectangle. Base times height is the whole rectangle. Triangle is half of it. And in general, you said a parallelogram actually. That's right. Leo Yu is right. In general, if I have a triangle, maybe the triangle looks like this. And then I can go and say that's going to be half of a parallelogram. I just copied it. But of course, then the question is, why is the area of the parallelogram base times height? The reason why the area of the parallelogram is base times height, the easiest way to describe that is just to think of a deck of cards. If you get a deck of cards, if you line it up all perfectly, you've got card, 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 just like this. But if you go and whack the deck of cards like this, then the deck of cards just kind of shifts over. And it has the same number of cards in it. The cards will still have the same volume. And in this particular case, this is sort of like taking a rectangle and then, bang, whacking it a little bit. So that would be why it's base times height. Okay. Eric Zhang asks, can you talk about 3D printing face masks? That's pretty interesting. Actually, there's a guy I know from high school. I mean, a long time ago when I went to high school with him, he's an interesting guy. And now he actually is making 3D printed clear face masks to go and help people during this coronavirus crisis. It's really inspiring. I see him posting about I think he's made several hundred of them at this point. So the answer is you can 3D print a lot of interesting things. And I guess the goal then is to figure out what to 3D print. What should you 3D print? And if you ever want to get into 3D printing, it's actually all about math and geometry. Okay, more questions. Temp ID says gas mask. That's a little bit harder to 3D print. Maybe I'll tell you why. If you're going to try to 3D print something, the material you use for printing comes out of something that you squirt. So it's good for building things out of some material that you'd squirt. But a gas mask is not designed to just be like a solid piece of material. That would be called a suffocation mask because you can't breathe anything. A gas mask, the whole point is that you have some kind of a filter. So you need to start using something called chemistry. You need to start using the different kinds of materials, like certain kinds of materials that, for example, when air passes through, maybe it has holes, but the holes are so small that they catch lots of things. Or you might even want them to contain certain kinds of chemicals that will react with whatever is coming through. So that would be not very easy to 3D print a gas mask. 3D printing is generally useful for printing things that are supposed to be solid. Maybe someday our technology will get good enough to print other things too. Math's genius. What is the biggest prime number? That's a famous question, by the way. There isn't one. There is always a bigger prime number. And in fact, there's a famous way to prove this. But first I should say, if you happen to know a very big prime number, that's useful. The reason is because prime numbers these days are related to what's called cryptography. In fact, even what you're doing right now, watching me on YouTube, the entire stream that you're watching is something that has been encrypted, meaning that stream has been made so that you can watch it, but your neighbor is not able to just kind of turn on their computer and look at whatever you're watching right now. And that's based on prime numbers. And the bigger the prime number that there is, the better your encryption is in those kinds of algorithms. Now, what is the biggest prime number? Watch, I'll show you why there isn't any. Let's pretend that there was only some prime numbers, that they stopped after a while. Here are some prime numbers, 2, 3, 5, and 7. Is 9 prime? No. So I must be done. These are all the prime numbers, right? Well, watch this. Suppose I pretended these are all the prime numbers. Not pretend. Oops, I wanted the eraser. If these are all the prime numbers, then you can calculate what happens if you just multiply them all together and add 1. 2 times 3 times 5 times 7, and then add 1. Okay. Now, again, the way this works is I said, if those are all the prime numbers, I can calculate this. Why is that relevant? The reason that's relevant is because look at what I've got. In what I've got is this, and somebody says it's, Andrew Shan says it's 211. I'm not promising 211 is prime because the thing I started with was an if statement. It was like, if these are all the prime numbers, and they're not. There are more prime numbers. But anyway, if these were all of them, this has something special. Whenever you take this number, if you take this number, is it odd or even? If I took 2 times 3 times 5 times 7 and then plus 1, is it going to be odd or even? Yes. Winter Rain says it can't be divided by any of the prime numbers! ! Exactly. So the point of this is if you go and multiply this all together, it can't be divided by 2 because this first part is divisible by 2 and you've got this annoying 1 left over. It's odd too. Thank you for saying that. But so if I have this, when I calculate that, I know a few things. Let's draw a rectangle around it. The rectangle is not divisible by 2. But it's also not divisible by 3. Because if I've got 2 times 3 times 5 times 7, that's already divisible by 3. It's 3 times something. And there's a leftover of 1. It's a remainder. So it's also not divisible by 3. It's also not divisible by 5. Because it already has 5 times some stuff, and there's a remainder. And it's also not divisible by 7. So look, I've just found a new number, which is not divisible by any of my previous prime numbers. What that means is that then definitely this new number is either prime by its own, or there's like another prime number that I haven't discovered yet. Does that make sense? So that's it. Oh no's. That's right. Thank you, Andrew Shan. So that's how you know that you can't have a finite list of prime numbers. If there was only so many prime numbers and then you stop, you say, no, you just made a mistake. Multiply all of those together, add 1, and that will either be a new prime number or there's some other prime number you haven't discovered yet. So then you might say, wow, that was cool. Thank you, Annie. I'm glad that you liked it. The first time I ever saw this, I also thought that was cool because you've just watched a proof. This is called a proof. This is where we explain how something is true. And the beautiful thing about this proof is that I actually didn't even tell you what the next prime number was. I just said multiply them together, add 1, and that's either prime or there's a prime that is a factor of it that you haven't found yet. And remember I said it's very important to find new big prime numbers for cryptography. But there's a problem. I mean, when I say there's a problem, well, yeah, there is a problem. It's hard to find prime numbers. But this gives you a way. Just take all the prime numbers you know, multiply them together, and add 1. Well, that doesn't work either. That's way too big. Because we didn't promise that that was a prime number. We just said it might have a new prime factor. So this is just showing how primes are somehow hard to find, but it's easy to show that there are infinitely many. That's a very weird situation to be in. To go and say, there are definitely infinitely many prime numbers, but I have a hard time telling you what the next one is. But that's what the proof lets us know. It lets us know there are infinitely many, even though I can't tell you what the next one is. More questions. John Senna, C-E-N-A, is John Chenna or Senna, asks, how are you so confident to answer any math question? It's because I'm willing to not be able to answer if I get stuck in the middle. You see, whenever I go and jump on one of your questions, I don't always already know what I'm going to do. I'm just kind of like, I think I'll try to figure this out. But I'm willing to get to a point at the end. If I ever got to a point where I said, yeah, this does look hard. I don't see what to do. Then I would just say, okay, that's interesting. That's a new thing for me to learn about. And then after the live stream, I'd probably go and try to learn it. So what I'm trying to show you is this is a certain mentality. It's like somehow, it's not really that I'm super confident that I can do everything. Rather, it's that I'm willing to try everything. And if I don't succeed at the end, I'll either ask all of you for help. Like I'll say, quick, someone help me Google it. Or I'll try to figure it out afterwards myself. But this is also showing you that I have no interest in doing the things that I already know how to do. It's like, that would be boring. I actually would find that very, very boring. So it's not the confident thing. It's like, I'm just going to go and try. I'm going to try. Well, I'll answer the other side though. It's like, why am I somehow willing to jump on camera in front of like 240 people and live stream to the world while I attempt to struggle with math problems? That one is something where I got a lot of the confidence or ability mainly from teaching. I actually really think that teaching is very, very interesting. I got involved in teaching when I was in 9th grade. In the United States, that's the beginning of high school. And I would go and help volunteer to coach my middle school math team. If you've been teaching and explaining things to other people for long enough, you start to become quite confident in understanding why everything is true. To me, the difference between confidence and not confidence is sometimes that, it's just like you just always do things this way. And if someone ever asked you, hey, why do you do it that way? Then you'd say, well, because you do. And I grew to not like that feeling. And that's what you get if you go and explain things to people. Because if you explain things to people who are your age, they're going to tell you, hey, I don't get it. Can you tell me why exactly you do that? And I'm not allowed to just go and say, well, because you do, right? I have to go and figure out why it's true. And so I would encourage you, if you want to kind of build that confidence and build that ability, get involved in teaching other people. You can teach your younger brother or sister. You can try to teach other people at your school. It's a lot of fun. More questions. Kelly Wang, how was P discovered? P? P. That's not a P. How was P discovered? Oh, that's still not a P. Yeah, so I actually have now finally figured out what's going on with my pen. It's that somehow if I move and touch the thing too fast, it jumps. But how was P discovered? So that's a good question. The reason I say that's a good question, you probably meant pi, but what I was wondering is I was kind of thinking like, why is the P written that way? I don't actually know. You see, because if you think about the languages and like where alphabets came from, we use this kind of writing for P, but this is like Latin. It's based in Latin. If you go and look at anything in Greek or you look at Russian, actually I don't know if Russian would you write it this way, but definitely Greek would write that for pi. So this would be the P sound. Actually, if you ever go to Greece and you look at the signs, it's very interesting. If you look at the road signs, at least for somebody who grew up doing a lot of math, when I went to Greece for the first time, I looked all around at all the road signs. I was like, it looks like math equations everywhere. They've got pi's everywhere. They've got like sigmas everywhere. They've got all the squiggly things, alphas, thetas, you name it. But somehow, that's how they pronounce pa. How did we get here? I don't know. That's a good question. That's a really good question. I'm curious. The reason I said I'm curious, by the way, is because there's something else. In Greek. In Greek, there's something that looks like a P. There's a lowercase rho. There's something that looks like that. But that sounds like R for us. So I'm actually kind of curious how this happened. I'm curious. I'll go take a look. All right. More questions. Daily challenge with Po-Shen Loh. Wow, it sounds like my team is asking me a question. Either that or there's some impersonators out there. Is pi even or odd? I would say it's neither. The notion of even and odd is only useful for whole numbers. As I said the word useful. It's like you can define anything you want, but it's most interesting to choose definitions for things that you can use for something else. And the deal with even and odd is that's telling you whether you can divide it evenly by 2. Like, that's why it's called even. You know what? Then maybe I would go and say, here's my answer. You want me to give you an answer? I'll give you an answer. You ask me, is pi even or odd? I'll say pi is not even. Is that good enough for you? Pi is not even. I'm not willing to say it's even because I can't divide it by 2. Even means I divide it by 2 evenly. But I'll give you another answer, daily challenge with Po-Shen Loh. I'll say pi is not odd. Because what does odd mean? Odd means that you divide something and you divide something by 2 and it leaves an odd one out. Have you heard this way of saying it in English? Like there's an odd one left out. And odd is like the odd one left out. So odd means when you divide by 2, there's a leftover of 1. So what this is saying is that actually there are things which are not even or odd, because here's one of them, it's called pi. And it's possible to have numbers that are not even or odd. In fact, those are all of the non-integer numbers. All the numbers that aren't like 0, 1, 2, 3, 4, or -1, -2, -3, and so on. And maybe since this thing came up, I'll finish with one of these like really funny sentences. Here's a sentence. This sentence is false. All right, is that sentence true or false? Uh-oh. So you're telling me this, so you're saying this green thing is false, right? So if the green thing is false, then this sentence is true. Oh no. Arg, paradox. Yes. Oh no, now we can't say it's false, because if we said it was false, then it would be this sentence is true. So it's true. But if it's true, then this sentence is false. Oh no, it's neither. So what that means, kapow, right? Indeed, this is one of these things that's neither true or false. I mean, I can show you something else that's neither true or false. Ooga booga. What does that mean? I have no idea. I just know that some people on the chat, which way is the chat? The chat's this way. Some people on the chat sometimes are just asking me about the ooga booga. I have no idea what you're talking about. So it's either true or false, neither true or false. I don't know. It's something. But the point is that you can write nonsense all you want. Sometimes there's nonsense and it's neither true or false. This is an example of nonsense, right? So that's also neither true or false. And the pi is neither even or odd. Okay. Right, and I guess that seems like a good way to finish with ooga booga, oompa loompa, and all of this. That will wrap up our week, or Friday here. As a reminder, we will have a weekend live stream. It's usually it's always at 8 o'clock p.m., 45 minutes, 8 to 8:45 p.m. Tomorrow, that would be Saturday night in the United States. Now, the topic that will be done there is something I have to figure out. I haven't figured that out yet. What makes the difference? What makes the difference between these daily ones and that weekly one is the weekly one. I'll probably talk about something that's related to what I've been thinking about, and I'll try to cook a math problem out of that. And then, of course, that one, we're not going to have these kinds of math questions that people ask. Afterwards, people will ask any kind of question that they want. And I will answer the non-math ones, because the math ones are reserved over for here. But anyway, so that was a good way to end the week. I wish all of you a very happy Friday, and good luck with everything that you're working on. See you.